Welcome to today's lesson on spontaneity for Chem Honors. Let's start off by talking about what the concept of spontaneity means, and then we'll talk about how to determine spontaneity for a particular reaction or process. So spontaneous isn't what it means when you're talking about a group of friends and just doing things because you feel like it. Spontaneous is a process that occurs, and it has to be able to occur under a given set of conditions without any outside intervention. And that usually, by outside intervention, we usually mean things like adding energy. All right, so a spontaneous process is one that you expect to happen just by mixing two chemicals together or by having a set of specific conditions. Spontaneous reactions will occur in one particular direction. For example, an iron nail will rust by reacting with oxygen. But if you have rust, you can't go back the other way. You can't then, at least not very easily, create oxygen and iron. Hydrogen and oxygen gas. So we have our reaction of hydrogen gas and oxygen gas will go forward, and should have a gas in there, sorry, to make two water, and can be gas or liquid. We'll say gas at this point. But water can only form from hydrogen and oxygen if you put electricity in. So that's the energy you have to put in. That's the outside intervention. So we'll draw a backwards arrow with an X through it, meaning it doesn't go in the reverse direction. Likewise, water will melt, ice will melt if you put it above 0 degrees. That's a spontaneous process. You'll never get ice to freeze, water to freeze above 0 degrees, at least not under normal conditions. And below 0 degrees, you'll see water spontaneously freezing into solid ice and not melting. So the concept of spontaneity then has to do with both the direction and the extent of a reaction, and the extent we'll get into in the next unit on equilibrium. And it's determined by our two driving forces of enthalpy and entropy. Now, we spent a whole bunch of this unit on enthalpy, so we're going to focus today on entropy and on another concept that enthalpy and entropy together create. So the driving forces of enthalpy and entropy both come about to help in determining spontaneity of a reaction. And it turns out that the enthalpy does have something to do with entropy, and the whole concept of a spontaneous reaction is that the entropy of the universe must go up. And this is our second law of thermodynamics. So the universe is always getting, as it were, more disordered, more spread out, more things, more ways of making things available to it. Okay, now, be careful, because we're about to come in the next part of this unit. We're going to come into the concept of rate of a reaction. And be aware that the spontaneity of a reaction doesn't necessarily indicate whether it's going to occur at any perceptible rate. So a reaction could occur so slowly that you can't detect it occurring. For example, wood burning. So you may have a wooden desk at home, and wooden desk, when it burns, it releases a lot of energy, and that's a great release of enthalpy. So a decrease in enthalpy, meaning that's going to be what we consider a favorable reaction. And it also releases a lot of gas, which we're going to find out is a great increase in entropy. So both of those things together do make wood burning a spontaneous reaction. However, it doesn't go very fast. And that's a good thing, because we would never have any wood around. And that different concept is reaction rates, kinetics, which is different from thermodynamics. And we'll bring all that in together when we talk about kinetics, starting in the next unit and next lesson, maybe even, I believe so. Okay, so let's go back to our idea of enthalpy. So enthalpy, delta H, has a favored direction of change, and that favored direction is exothermic. So why is an exothermic reaction favorable? So remember, exothermic means that the delta H is less than 0. It means it's negative. So the system is losing potential energy. And as we've been discussing, that potential energy doesn't just disappear. It has to be converted into a different form of energy. And so it's released as heat. But where does that heat go? That heat goes into the surroundings. So the surroundings increase temperature. The temperature increases. And what it turns out is that that increases the entropy of the surroundings. And that's really why delta H, negative delta H reactions are spontaneous. Now, having or favored, I should say. So having a favored enthalpy is good. You need to have that in general to help, but it's not enough. You also need to take into account the entropy. And we've talked about this before. Entropy is indicated, or the change of entropy is indicated by delta S. And it's kind of obscure why it's an S, not an E. E could be energy, other reasons. They're not really sure why an S, but they can say why it's not an E. And the favored change for entropy is always increasing entropy. So we want to increase. Now, this favored, we can do things that decrease in entropy. We'll talk about that in a few minutes. But we want to increase entropy or get to, as we said, sorry about that, we want to get to more disorder. I mentioned before that a perfect crystal at absolute zero has zero entropy. That's the third law of thermodynamics. And it's rather obscure for us. We don't really need to worry about it. All it is really saying is that you can actually get to a state of zero entropy, or you can envision a state of zero entropy. Getting there is a little more tricky for many different reasons. So one of the things I'm going to ask you to do is to take a look at a system and predict the sign of the change in entropy, whether it's a positive or negative. Positive meaning increasing entropy. So moving from solid to liquid to gas is always going to be a change of entropy because we're getting more disordered. So on the right here, we see a solid going to a liquid and a liquid going to vapor. And then, of course, going directly from the solid to the vapor should also have an increase in entropy. So moving forward, going to the right on all of these things is going to have a positive delta S. Dissolving solids into the solution. So this is letter C here, because this is getting more spread out and giving us a larger state, a larger way of doing things, more ways of doing things, more disordered. So that's a positive delta S on letter C as well. Adding heat. So what does heat do? That's an increase in temperature. So temperature is going up. Delta T is positive. That increases all sorts of energy: kinetic energy, energy of motion, vibrational energy. Molecules aren't just sitting there. Their bonds are vibrating like little springs, and they vibrate and they rotate and they do all sorts of neat things. And that's all energy. And increasing the heat increases all that, the energy content, and increases the delta, increases the entropy as well. And so that's D down here. So we have a positive delta S all the way along. So we have several ways of looking at just a particular process. Now, we do have reactions that we're going to look at. And one of the things about a reaction is that we have a positive delta S if we have an increase in the number of moles of gas. This is because gases have the highest, by far, the highest entropy of any solids, liquids, or gases. Now, moving in that direction for anything is going to, for solid to liquid, liquid to gas, solid to gas, that's always going, or solid to aqueous, that's always going to do it. But gases are going to give us the biggest example. So in the first reaction, what we're going to do is we're going to count up the number of moles of gas. In the reactants, we have 2 moles of gas. In the product, we have 1 plus 3 is a total of 4 moles of gas. So the moles of gas in the product is greater than reactants, and so that's a positive delta S. In the second example, we have 0 moles. Be careful, this is a solid. We have no moles of gas. Here we have, even though there's a 2, that's still 0 plus 1. So the product is still greater than the reactants. And so we have a positive delta S. Obviously, going in the other direction would cause a decrease and a negative delta S. And if we have even number of moles, so if we have a particular reaction where I have even number of moles of gas, then you can't tell. We don't have enough information. Unless we get a little bit more specific about it, we don't really know. I also wanted to mention one thing that's not on here. So dissolving a solid into a solution is a positive entropy change, but dissolving a gas into a solution, because gases are the highest, a gas going into a solution is a negative delta S. And this is a big reason why gases have a lower solubility at higher temperature, because as you increase the temperature, you're increasing the entropy and you're driving it more towards that gas state. So let's do a little bit of practice here. And if you want to stop the video right now and take a look at these three reactions and see if you can figure out whether the entropy is increasing or decreasing. Is it positive delta S or a negative delta S? All right, so either you stop the video or you just want to keep going. So let's take a look. In the first reaction, we have 2 solids, no gases. In the reactants, on the right side, we've got 2 gases. We also have an aqueous and a liquid. So we're going up in entropy no matter what. And so this is, oh, I'm sorry about that. So we're going up in entropy, and I have an increasing entropy with a positive delta S value. I'm going to turn my phone off. There we go. Hopefully I got it. In the second reaction, crystallization. Crystallization is going from an aqueous, so we're taking something that's dissolved into a solid. So we're going the opposite of what we talked about up above. It's going from more disordered to less disordered, or let's call it more ordered. So more ordered is a decrease in entropy and a negative delta S. And finally, water freezing, going from a liquid to a solid. Again, we're getting more ordered. And because we're getting more ordered, we have a decrease in entropy or negative delta S. Now, obviously, we can freeze water at a particular set of conditions. So even though we have an unfavorable entropy change here, there is a way of getting that reaction to move, or that process to become spontaneous. And if you think about it for a moment, and we'll talk about that particular process in a little bit, you'll see exactly how this makes sense. So we have 2 cases, or two things to worry about in determining the spontaneity. And both of these, the delta H and the delta S, are eventually going to come into, and we'll see this on the next page, a concept of what's called Gibbs free energy, which is a way of looking at the system and knowing, based on the delta H, delta S, and the temperature, whether or not the system is spontaneous. So it depends on enthalpy, entropy, and let's put temperature in there as well. And that's going to be a big one for us. So in case 1, we're going to have a negative delta H, and we're going to have a positive delta S. These are both favorable. So that's exothermic reaction. So favorable and favorable. And so what's going on with the delta S? There's less potential energy. It's more stable. In the delta H, delta S, there's more disorder. So those two things combine to make a something that is always spontaneous. And I'm going to introduce this now. We'll see this on the next page. The delta G is going to be a negative value. It's going to be a calculation for us. So in case 2, we're going to go to the opposite direction. We're going to make both of these unfavorable. So unfavorable means that we have a positive delta H. So we have an endothermic reaction. And we have a negative delta S. Again, unfavorable. Unfavorable. And so what's going on? We're increasing the potential energy. We have to put energy in for this to happen. And it's less stable. Here with the delta S, we're getting less disorder. And if we have 2 unfavorable processes, this is not spontaneous. It's never going to be spontaneous. The delta G is positive, although it is spontaneous in the reverse direction. And we're going to start to see the concept of reversing reactions as well. So now we've got our 2 cases where the spontaneity ends up being dependent on the temperature. In case number 3, let's make the delta H, exo not endo, be negative and make that favorable. And so we have that increase in potential energy. And over here, we're going to make the delta, that should have been a negative up there. And we're going to make a positive delta, I'm sorry, this is going to be a negative delta S. So this is unfavorable. So now we have one being favorable, one being unfavorable. And what it's going to turn out is it's going to depend on the temperature. The delta S is going to turn out is the delta S term becomes more important at high temperature. So if the negative delta S becomes more important at high temperature, as temperature goes up, this becomes unfavorable. So this is going to be unfavorable at high temperatures. Now, what things do you know that are favorable at low temperatures? Well, things that are favorable at low temperatures are things like freezing. So if we look at freezing, why does that work? So freezing is an exothermic process, but the delta S is negative, right? It's going from a liquid to a solid. So it's exothermic, but going from a liquid to a solid. Remember that freezing is spontaneous below 0 degrees C. And so this is a process which can be spontaneous, even though it has a negative delta S. It can be spontaneous at low temperatures. All right, well, if you've been paying attention to the symmetry we've seen so far, we'll know that a delta H that's positive and endothermic, and that's unfavorable, coupled with a positive delta S that's favorable, is also going to depend on temperature. Depends on temperature. But again, this still is more important at high temperature. So if the favorable one is more important at high temperature, what that means is that as the temperature goes up, the reaction becomes more favorable. And so delta G becomes negative at high temperatures. And so what's a process that's favorable at high temperature but not favorable at low temperature? Well, how about boiling? Boiling, we know that's an endothermic process, but we also know that we're going, oh, what happened to my BOI? We also know that we're going from a liquid to a gas, which is a big positive delta S. And so this is spontaneous above 100 degrees C. And we have our concepts in place. Now, these concepts can be translated into a mathematical equation, which you're starting to see. And if you turn over your page, you will see it in a concept called Gibbs free energy. Delta G, Gibbs, hey, something that makes sense, right? Gibbs free energy is a measure of the spontaneity. So the delta G, and this equation is on your reference chart, so you never have to memorize it. Delta G is equal to delta H minus the T delta S. And there's that temperature coming in that I talked about. The temperature has to be in Kelvin so that we always have a positive delta T, and so that when you multiply it by the delta S, it just doesn't change the sign at all. So in case one before, we saw that both of these were favorable delta H, favorable delta S. So delta H was negative, delta S was positive. But what happens when you take a negative, the negative minus a T, and you multiply it by a positive? Well, you get something that's always negative. A negative plus a negative, right? So let's make that a plus and a negative. A negative plus a negative is always going to be spontaneous, and delta G is always going to be less than 0, negative. In case 2, we had the opposite. We had both of those being unfavorable and unfavorable. So we have a positive delta H. That's not good because the delta G automatically now is going to be starting with something that's not favorable. Let's put a plus and a minus here. We're going to subtract off the temperature times a negative delta S. So we have a positive plus a positive. So positive and a positive. This is never spontaneous because delta G is always greater than 0 or positive. All right, case number 3, as I indicated, we have an favorable delta H and an unfavorable delta S. And so the favorable delta H is negative, which is good. But then let's put a plus there and a minus. And so we have minus T. So the T is always getting a negative sign and a negative delta S. This becomes a positive. So when this term becomes big enough, as T goes up, delta G becomes positive. Delta G becomes a positive value. So this is the delta H then becomes more important at low temperature. And so this reaction is spontaneous at low temperatures because the negative delta H is important. All right, so delta H, we are, well, I talked about this, we're forming bonds. And so forming bonds is exothermic, but we're also making it more ordered, and we need to reduce the temperature for that to happen. Finally, in case number 4, we went the opposite way from case number 3. We had an unfavorable delta H and a favorable delta S. So our positive delta H, make that positive and negative, negative T, and a positive, that should be a negative T, delta S. So again, this becomes larger as T goes up. And so the delta G becomes negative, right? We're subtracting a larger number. So delta G becomes negative as T goes up. So that's why this reaction is now spontaneous at higher temperatures. And here I've got the example of ice melting, but I used the example of water boiling before. It's the same concept. This is an endothermic process, so we need to make that entropy more important, that increase in entropy more important, and we do that by raising the temperature. So the Gibbs free energy is all about how much energy is released during a process. Now, we have this concept in chemistry, and we'll get more into this in a few lessons, I'm not sure exactly when, where we talk about what are called standard conditions. Now, standard conditions are just a way of knowing that we're always talking about the same thing. So you can always have different concentrations of products and reactants in a reaction. And if you have the products and reactants in which the standard conditions have 1 molar concentrations for all solutions and pressures of 1 atmosphere for all gases, and I should put in there somewhere, solids and liquids are pure. So if you've got those things present, then we can put this little naught sign, and we call it the G naught, the delta H naught, and the delta S naught. And all that means is that we've got standard conditions. A lot of the tables and the thermodynamic quantities that we get are measured at standard conditions. Okay, essentially standard conditions, you're starting with basically equal amounts of reactants and products. I know it sounds like a strange place to start, but that's what's going to tell us whether the reaction is going to move in the forward or the reverse direction. So what we can do is we can apply our delta G equals delta H minus T delta S equation as long as we're given the delta H naught and the delta S naught of the equation the process that we're looking at. So we're always going to use 25 degrees C as our standard, not because that's a standard, but just because that's where a lot of these were measured. We're going to assume that the quantities don't change as the temperature changes, and that's going to be important in part B. So, is the reaction spontaneous? So you can see that the delta S is positive, which means that this could be spontaneous. It could not be spontaneous depending on the temperature. So we have to do a little calculation. So let's plug in our delta G naught is equal to delta H naught minus T times delta S naught. Temperature 25 degrees C is going to be 298 Kelvin. Don't forget to do that conversion, just like the gas laws. So we plug in delta H is positive 135.5 kilojoules per mole, minus the T is 298 Kelvin. Now, the delta S naught, be careful, the delta S naught is in joules per mole. So what we have to do is make sure that we convert that joules to kilojoules. Otherwise, you're not going to be matching up, and it's going to be like trying to add, if you have 1 penny and $1, it doesn't give you $2, right? So if you have 1 joule and 1 kilojoule, it doesn't give you 2 kilojoules. You got to be careful about things like that. So dividing by 1,000, and notice also the unit, there's a K in there to remind you that you need the K to cancel out. We have 0.1488 kilojoules per mole times Kelvin. Okay, so now let's do a little math here. Let's cross off, or let's cancel out the kelvins so that we know that those go away. And let's finish up the mathematics. We have 135.5 kilojoules per mole. If you calculate the second term, it turns out to be 44.3 kilojoules per mole, which is positive 91.2 kilojoules per mole for the delta G. And because that's positive, excuse me, positive delta G means This is not spontaneous. Now, here's a cool thing. We know that this is going to become spontaneous at a higher temperature. How do we know that? Because we know that the T delta S term is going to become larger. So let's see what happens at a higher temperature. At a higher temperature, we still have the same delta G and delta S. So the delta G naught is 135.5 kilojoules per mole minus 900 degrees Celsius is 1173. Like I did that fast math there. 1173 Kelvin, just add 273 times that same 0.1488 kilojoules per mole. Okay. Cancel out the K's. We still have the same delta H, 135.5 kilojoules per mole. But now the T delta S term, we're subtracting off 174.5 kilojoules per mole. And without doing the calculation, you can see that's a negative number, negative 39.0 kilojoules per mole. Oh, I wanted to box that. Kilojoules per mole. And so the delta G is negative. I'm sorry, negative delta G. So it's spontaneous. So this reaction is spontaneous at higher temperatures, yes. Now, here's the cool thing. We can figure out, okay, since it's going to be spontaneous at higher temperatures, we want to go above a certain temperature. What temperature do we want? We want the temperature where delta G goes from positive to negative. Well, where does that happen? It happens when delta G equals 0. So what we're going to do is we're going to put T as our unknown. And we want delta G, let me say delta G naught, sorry, delta G naught. Delta G naught, I got to put the knots in there, I keep forgetting. The delta G naught now is equal to 0. I'll put in the kilojoules per mole. And we have our 135.5 kilojoules per mole for our delta H minus T, which we're now going to solve for, times 0.1488 kilojoules per mole times Kelvin. Rearranging that, we have, I guess I should have rearranged it first. So if we start off with 0 equals delta H naught minus T delta S naught, we're going to rearrange that so that we have T times delta S naught is equal to delta H, or temperature naught is equal to delta H naught divided by delta S naught. That's probably a better way of doing it. I should have done that first. And so we have positive 135.5 kilojoules per mole times mole, sorry, no Kelvin there, divided by 0.1488, which you can see is going to be a large number, kilojoules per mole times Kelvin. There's our Kelvin in the denominator that comes up to the top. And that now gives us 910.6 Kelvin, or 637.6 degrees Celsius. Okay, so we need to get up above that temperature. And the reason we need to get up above that temperature is because of the positive delta S favoring us. Okay, now, if we ever ask you to do a calculation like this and you get a negative temperature, oh, there's my BOI. How did that get down there? So if we have a negative temperature, okay. I just love it when it does this to me. Oh, the joys of Word. What happened to my temperature there? What happened to my... Okay, where delta... Come on. I just touched it lightly and it goes. I'm sorry about this, guys. So the delta G naught, temperature, I want, where that's right, the delta G naught, where's my, and delta G naught goes from positive to negative. All right, and that temperature was 910.6 Kelvin. All right, hopefully that doesn't get lost now. All right, so let's take a look at this reaction here. So we've got a reaction. There's our delta H. So we're giving it to you in the reaction, and there's our delta S naught, or delta H naught. So the delta H naught of this reaction is exothermic, right? So we know it's exothermic because it's a product, and so the delta H naught is negative 85 kilojoules. And the delta S is negative. Look at what we've got here. We've got 2 moles of gas going to 1 mole of gas. So 2 moles of gas going to 1 mole is going to be a decrease in entropy. So let's think about this for a moment. Is this going to be spontaneous at lower temperatures or at higher temperatures? So at lower temperatures, the delta H, remember, is more important. As you get to higher and higher temperatures, the delta S is going to be more important. And so that negative delta S is more important at high temperatures. So this reaction is going to be spontaneous at low temperatures. So at low temperatures, the delta H term is larger than the T times delta S term. And you can think of it that way as well, in terms of absolute value. Now, so we know that it's going to be spontaneous below a certain temperature. What temperature? Again, set delta G naught equals to 0 equals delta H naught minus T times delta S naught. And that gave us before that the temperature, we rearranged it above, is the delta H naught divided by the delta S naught. And the temperature is negative 85 kilojoules divided by negative 190. I almost messed up. That's joules, so 0.198 kilojoules per mole times Kelvin. Let me make that 0 look more like a 0. Notice they're both negative, and that's going to be true for all of these problems, where if they're both negative or they're both positive, you're going to get a positive K. So we have negative 85 kilojoules divided by, actually that should be, there's a mole there, that should be per mole. So let's put the per mole in there. Kilojoules per mole. And, what am I doing that again for? I don't need to do that again. And so we get a temperature of 430 Kelvin, or 157 degrees C. And that's where we're going to be spontaneous below that temperature. Okay, so we've got a whole bunch of concepts here about spontaneity of processes. Please watch this again if you're not quite sure, and I hope that the homework makes sense for you. Have a good day, and we'll see you in class.